Part 2 of energy transformations, heat. You'll never forget this equation. Heat is Q equals MC delta T. My name is Michael Claudy. MC delta T. That's my rap name. I'm so hot, I'm cool. I'm so cool, I'm hot. Okay? This is a heat formula. Just to be pestilentially different from everyone else, chemists had to go ahead and call energy Q when physicists had used E or W. But we can live. M, how much of something are you heating? 1 gram? 100 kilograms? Delta T, how hot are you planning to make it? And the letter C is the specific heat capacity, hence C, is how much does this substance need to warm it up. This makes pretty good sense. If this answer is in joules, and this is kilograms or grams, and this is degrees, then this thing has to have joules in it to give you the correct answer, and it has to divide out the mass and temperature. This gives us the units of joules per degree per gram. That makes common sense. How many joules do I need to heat this substance per degree per gram of substance? So we'll make some tea with the formula. We're going to assume our water starts at 20 degrees and is heated to 95, which would be, 75 degrees warming. Now, a cup of liquid is 250 milliliters by definition. For water at 20 degrees Celsius, 1 milliliter is the same thing as 1 gram. Only for water and at 20 degrees. You can use this throughout any temperature regime we have, from 0 to 99, because it's really not much of a density change. Does not apply to alcohol, gasoline, other liquids, just water. So 250 milliliters of water is effectively 250 grams. We go search for the heat capacity of water, and we get 4.2 joules per degree per gram. Take our formula, plug in our numbers. There's the heat capacity of water, our mass, and our temperature change. Since we've looked this up per gram, we can leave that in grams. Be careful. Sometimes it will say per kilogram. And I get this energy. Now, this, if you just move this over 1, then you've used up one of these 4 zeros, and you're down to 3. And 3 zeros have a nickname, kilo. So this is 78 kilojoules. That's a very straightforward formula to use. What happens if you're setting it on fire? When you set it on fire, then it's called combustion, not warming. And there's only 2 things that matter. The mass and what is it? Right? Temperature change is irrelevant. You're setting it on fire. It's going to burn at its combustion temperature. So the specific heat of combustion is in joules per kilogram. It makes a lot of common sense. So when we fire a gun or a rocket, the initial energy is going to be chemical. It's going to be all this. And that's what the rocket or the gun has to turn into kinetic. So the combustion formula links the chemistry behind many of our engines to the actual motion. So it's a fairly important one. So let's see how much fuel is needed to accelerate a van to highway speed. We'll use a Honda Odyssey again of 2,200 kilograms. Highway speed is this. Therefore, we'll look up the fuel combustion of these 2 fuels here. So if I want to get my car up to highway speed, I'm going to need 844,000 joules of chemical energy. Now, for gasoline, the energy is 45 million joules per kilogram. That's the specific heat of combustion here. Put it through the formula, and you get 18.7 grams of gasoline to get the car to highway speed, which is very close to what we got when we did this in the work section. We're just approaching it now from kinetic energy instead of generalized work. If we switch to hydrogen fuel, look at this number. It's almost 3 times greater. So not surprisingly, we need about 3 times less hydrogen instead of gasoline. Hydrogen would be an amazing fuel, pound for pound. Why aren't we using hydrogen then? There are a couple of problems. Gasoline starts from oil found in the earth. Hydrogen has to be made from water, and that takes as much energy as we get. So if you hooked up a generator at home using your wall socket and you generated hydrogen using electrolysis, you wouldn't save yourself a dime because the hydrogen fuel would cost you electricity. So we have this thing that it's found in nature for gasoline, and it's not found in nature for hydrogen. But look at the energy density per liter. There are 2 things we have to consider when we're using an item: how much it weighs and how much volume it takes up. Hydrogen is 3 times bulkier than gasoline in terms of storage. So if you could have liquefied hydrogen in your car, okay, its tank would have to be 3 times more volume. So 2 liters of gasoline would get you as far as 6 liters of hydrogen. And liquefying hydrogen and storing it in a tank is not cheap. You would need a tank more structurally sound than a welding cylinder, and it would be at unbelievably cold temperature when it was filled. So hydrogen has a bulkiness problem that we have not solved, and getting it is the problem too. Now, how much of this actually got used in the car? Typically, most cars only use about 25% of their available energy to move forward. So out of all that energy in this problem, the 20 grams of fuel, only 1/4 of it appeared as motion. So it really means to get 20 grams of gasoline available for motion, we'd probably need 80 grams or better before we could actually see that. And this chart is the efficiency of the engine. It does not bring into account air resistance. And so you're looking at probably no more than 10% of the gasoline you use winds up being useful to you. The bulk of it goes out the tailpipe as heat, and then there's a lot to fight air resistance. But this gives you a theoretical calculation of the efficiency of an engine itself, and it allows you to downgrade your totals of energy. Using a simple chart like this, you can quickly convert to your useful component.